Okay, think about really complex 3D shapes for a second. Maybe flowing fabric or the inside of some intricate machine part.
Yeah, capturing those accurately digitally, that's tough.
Exactly. Traditional methods, they often, stumble, especially with things like open surfaces, clothing, or fine little details. If you've ever wondered how we get past those hurdles to get really high fidelity 3D stuff, well, you're in the right place.
And it's fascinating because a team of researchers from Tsinghua University, VST, and the Chinese University of Hong Kong, they've just put out a paper on a new solution. It's called SparseFlex.
SparseFlex. Okay, we've got the paper right here. SparseFlex, high resolution at arbitrary topology 3D shape modeling, plus our own notes pulled together. So for everyone listening, our goal today, our deep dive, is to really understand what SparseFlex is about. We want to get into the more academic side, the core ideas, and especially what's genuinely new here.
Exactly. We want to unpack how it pulls off these high-res 3D models, even with those tricky arbitrary topologies, the open surfaces, the complex insides, without getting totally bogged down in the weeds.
Right, let's dive in. The paper itself kind of kicks off by setting the scene, talking about what's out there now and, well, where it falls short. What are the big limitations that SparseFlex is trying to tackle?
So if you look at the landscape of 3D generative AI, the authors point out that a lot of methods, especially ones using implicit fields, think sign, distance functions, occupancy fields, that sort of thing,
Okay.
they often have this, let's say, problematic two-step process. First, you need to take your raw 3D data and somehow force it into being watertight, completely closed, no holes.
And that's tricky.
It's not just tricky, it's computationally heavy. And crucially, you can lose fine geometric details in that conversion. Imagine trying to perfectly seal up, I don't know, a delicate piece of lace. You're bound to smooth over some of the important bits.
Lots of detail. Okay, that sounds like a pretty major drawback. What's the second step then?
The second part is extracting the actual 3D mesh from these learned and implicit fields, often using something like marching cubes. Now, that works okay sometimes, but the extraction itself can add its own little inaccuracies, artifacts, moving you further away from the original high-fidelity shape.
Right.
They also mention unsigned distance fields, UDFs, which can handle open surfaces better, but they often have stability issues during training, and they still struggle to capture those really subtle geometric features accurately.
So we're kind of stuck between losing detail by forcing things closed or struggling with stability and precision if we try to keep them open. Now, the paper mentions rendering-based supervision as a potential path forward. What's the idea there?
Yeah, this gets to a really fundamental question. How do we actually teach these models what a good 3D shape looks like? Rendering-based supervision flips the script a bit.
Okay.
Instead of directly comparing a generated 3D shape to a target 3D shape, you compare 2D images. You render the generated 3D model from different viewpoints and compare those pictures to ground truth pictures.
Okay. Comparing pictures instead of meshes.
Exactly. And the big advantage is that rendering is usually a differentiable process. That means you can figure out how small changes in the 3D model affect the 2D image and use that difference, the error, to guide the learning and refine the 3D shape.
That makes sense. And it avoids that forced watertight step you mentioned.
Precisely. It bypasses that initial lossy conversion, which helps preserve those fine details. It's sort of like sculpting by constantly checking the shadow your sculpture casts, rather than trying to measure the sculpture directly all the time.
Okay, neat analogy. So if it's got these advantages, why isn't everyone just doing this? What's the catch?
The catch, and the paper spells this out clearly, is memory, the computational overhead. Especially if you're using dense representations like a full grid of voxels and you want high resolution. Rendering from that kind of dense, high-res representation takes a ton of memory and processing power. It becomes prohibitive. You hit a wall in terms of the fidelity you can actually achieve because you just run out of resources.
The classic trade-off, more detail means more computation. So this brings us back to SparseFlex. How does it break through this limitation? What's the core innovation, especially from that academic perspective?
Right. This is where SparseFlex really makes its contribution. The central idea is introducing a fundamentally sparse voxel structure. So instead of filling the entire 3D space with voxels,
Like a dense grid.
exactly. SparseFlex uses a much smaller, strategically placed set of voxels, mainly concentrated around the actual surface of the object.
Sparse voxels. Okay, so focusing the compute power just where it's needed. How does that give such a big advantage?
Precisely. Two huge benefits. First, it slashes memory usage dramatically. This lets them model things at much higher resolutions. They show results up to 1024 cubed, which is pretty impressive.
Wow, okay.
Second, because it's not representing all the empty space inside or around the object, it just naturally handles open surfaces. There aren't any voxels defined in the empty regions, so there's nothing to force closed. The topology can be arbitrary.
That's a really elegant way to handle the open surface problem. Now, SparseFlex, it doesn't come out of nowhere, right? The paper mentions a connection to something called Flexicubes.
That's right, it builds on Flexicubes. Flexicubes is known for its accurate and, importantly, differentiable way of extracting surfaces, isosurfaces, from voxel grids. It uses something related to dual marching cubes.
Differentiable. That connects back to the rendering supervision.
Exactly. Flexicubes provides a high-quality way to get a mesh from voxels, and crucially, the whole process can be plugged into gradient-based optimization, which you need for that rendering supervision.
Okay, so SparseFlex takes the accuracy and differentiability of Flexicubes, but makes it way more efficient and capable of handling open surfaces by using this sparse voxel idea.
Got it. How is this sparse structure actually defined, mathematically speaking? What are the pieces?
So the SparseFlex representation, they call it script S, is defined by three key sets. First, script V, which is just the 3D coordinates of the centers of these active sparse voxels. Okay, the locations.
Then you have script F sub C. This stores the sign distance function, or SDF, values and also deformation vectors at the corners of the grid cells associated with these voxels. The SDF tells you the distance to the surface, positive outside, negative inside, crucial geometric info.
Right, SDFs are common. And deformations.
Yeah, they allow for finer details. And finally, there's script F sub Z, which holds interpolation weights for each voxel. These are used to reconstruct the smooth surface between the voxels. So basically, SparseFlex packs geometry and detail information efficiently into just these active sparse voxels.
SDS values, deformations, weights. Sounds like each active voxel carries quite a bit of information. But the key insight is that the number of these active voxels is way, way smaller than in a dense grid at the same resolution. That's the memory saving.
That's exactly it. The paper shows quantitatively that the number of SparseFlex voxels, N sub V, and the related corner grids, N sub C, are significantly lower than for dense Flexicubes at the same resolution. That's the core of the efficiency gain. And because it inherits that differentiable surface extraction from Flexicubes, you can still effectively optimize the underlying mesh using those rendering losses.
This really does sound like a fundamental step forward in just representing complex 3D shapes. Now, they also talk about something called frustum-aware sectional voxel training. What's the academic thinking there? Why is that significant?
This is another really key innovation, and it's crucial for making high-resolution training practical. Even with the sparse structure, trying to render the entire thing at, say, 1024 cubed resolution for every single training step can still be too much.
Still too heavy.
Right. Plus, standard rendering supervision usually only gives you learning signals for the parts of the object the virtual camera can actually see in that view.
Makes sense. If a part is hidden, the rendered image doesn't tell you much about it directly. So how does this frustum-aware thing work?
They took inspiration from techniques used in real-time graphics, like visibility culling. The idea is, for each training step, you only actively consider the SparseFlex voxels that actually fall inside the virtual camera's viewing frustum, that pyramid or cone shape representing what the camera sees.
Okay.
You extract the surface and render only using that relevant subset of voxels. By focusing computation just on what's relevant for the current view, they massively reduce the workload for each training iteration.
So it's like only activating and training the visible slice of the model at any given moment.
Pretty much. And to make it even smarter, they use an adaptive mechanism to adjust the near and far clipping planes of that frustum dynamically. This helps keep a roughly consistent, manageable number of voxels active in each step, optimizing memory use throughout the training.
That's clever. Really tackles the memory bottleneck head on. But wait, the abstract mentioned something about reconstructing mesh interiors using this. That seems counterintuitive if you're only looking from the outside. How do they manage that?
Ah, yes. This is one of the most, I'd say, academically novel contributions. It's really interesting. By cleverly placing the virtual camera inside the object sometimes.
Inside.
Yeah, or by carefully setting the near clipping plane so it cuts through the mesh, the frustum-aware training can actually focus on and supervise the internal structure using only those rendering losses.
Whoa. So you can learn about the inside just by looking at how light interacts with the surfaces revealed by the clipping plane?
Essentially, yes. It's a way to get information about internal geometry just from surface rendering. This is a big departure from methods that need explicit interior models or assume everything's solid. It could be huge for modeling things with complex internal structures like engines or biological systems without needing full 3D scans of the inside.
That is genuinely innovative, a really smart workaround. Okay, so we've got this efficient sparse representation and a clever view-dependent training strategy. How do they package this all up? The paper mentions a SparseFlex VAE architecture.
Right. So they take these core ideas, the SparseFlex representation, the frustum-aware training, and build a variational autoencoder, a VAE, around them. The goal of any VAE basically is to learn a compressed, meaningful, latent space representation of the input data. In this case, 3D shapes encoded using SparseFlex.
And for listeners maybe less familiar, a VAE has two main parts, right? An encoder that squishes the input data, the 3D shape here, down into a compact code.
Capturing the essence of the shape.
And a decoder that takes that code and tries to rebuild the original shape. And the variational bit lets you generate new shapes by playing around in that compressed code space.
Exactly. So the SparseFlex VAE's encoder starts with point clouds as input, usually with surface normals included. It first voxelizes these points into that SparseFlex structure we talked about.
Okay.
Then a relatively simple point net network looks at the points within each active voxel to extract local geometric features. These local features, plus information about how the sparse voxels are arranged spatially, get fed into a sparse transformer backbone.
A sparse transformer makes sense given the sparse input.
Right, it's designed to efficiently handle that irregular sparse data structure. And the output of this whole encoder process is that compact latent code representing the shape.
Got it. So how does the decoder rebuild the high-res shape from that compressed code?
The decoder takes that latent code, runs it through its own series of transformer layers, and then a final linear layer predicts all the parameters needed to define a SparseFlex instance. So it predicts those SDF values, the deformation vectors, the interpolation weights for all the sparse voxels.
Okay. Now, the paper also mentions self-pruning upsampling modules in the decoder. That sounds important for getting the high resolution and maybe dealing with those open surfaces cleanly. How do those work?
Yes, exactly. To get to high resolutions, the decoder uses two of these special convolutional upsampling modules after the main transformer layers. They basically increase the resolution by subdividing the existing voxels into smaller ones.
Upsampling makes sense.
But here's the clever bit. They also predict an occupancy probability for each new little subvoxel. If the probability is low, meaning the model thinks it's empty space, that subvoxel gets pruned away, removed.
Self-printing.
Exactly. This keeps the representation sparse even as the resolution increases. And it's particularly good at cleaning up the edges of open surfaces by getting rid of stray voxels that might appear in empty space.
So the whole thing, point cloud in, sparse voxels, encoder, latent code, decoder, upsampling with pruning. Out comes the high-res SparseFlex representation. It's all trained end-to-end with those rendering losses and the frustum-aware strategy.
Yes, it's a very tightly integrated system. That end-to-end training is key. And they don't stop at just reconstruction. They also show how this trained SparseFlex VAE can be used as a powerful building block for generating 3D models directly from 2D images.
Oh, okay. That moves towards really practical uses. How does that image to 3D generation work?
It's a two-stage pipeline they propose. First, there's what they call a structure flow model. This involves another separate 3D convolutional VAE, but operating in a lower resolution dense voxel space, combined with something called a rectified flow model.
Okay, a bit technical, but the goal is?
The goal is to take features extracted from the input image. They use a pre-trained model called DNAV2 for this and predict a coarse, low-resolution 3D volume that captures the basic shape seen in the image.
Got it. So step one, get a rough 3D shape from the 2D image. What's stage two where SparseFlex comes in?
Stage two is the structured latent flow model. This is another rectified flow model, but this one operates in the learned latent space of the SparseFlex VAE we just discussed.
Ah, in the compressed code space.
Exactly. It takes the coarse 3D structure from step one and the image features from DNAV2, and its job is to generate a detailed latent code within the SparseFlex VAE space. This code represents a refinement of the initial coarse shape.
Okay.
Then finally, you feed this refined latent code into the decoder of the pre-trained SparseFlex VAE, and out pops the high-resolution arbitrary-topology 3D shape.
Wow, okay. That's quite a pipeline. In for core structure, then refine it within the powerful learned space of the SparseFlex VAE to get the high-fidelity results. So how well does it actually work? The paper presented some results, right? What did they find?
The results are actually quite impressive. They show state-of-the-art reconstruction accuracy for a VAE on several pretty challenging datasets: Toys 4K, Dora Benchmark, and Deep Fashion 3D. Quantitatively, they report really significant gains over previous methods, something like an 82% reduction in Chamfer Distance.
Which measures shape similarity.
Right, lower is better, and about an 88% increase in F-score, where higher is better. These are big jumps, indicating a substantial improvement in how accurately they can reconstruct the ground truth shapes.
Those are genuinely remarkable numbers. And did they specifically test this on datasets with lots of open surfaces, since that was a key motivation?
Yes, absolutely. They paid close attention to the Deep Fashion 3D dataset, which is full of clothing items, classic examples of open surfaces. And their results there also significantly beat existing methods designed for non-watertight shapes.
That's crucial validation.
Definitely. And beyond the numbers, the paper includes visual comparisons showing their image to 3D results on various in-the-wild images. You can really see the ability to capture sharp features and fine details, even on complex objects with open parts, which is often where other methods struggle.
Yeah, the visual results in the paper are quite striking. You see a level of detail, especially on things like garments, that looks much better than what we often see. Now, like any good research, they also mention limitations, right? Where do they see room for improvement?
They do. They point out a few things. One is that even with the self-pruning, the boundaries of open surfaces can sometimes still have minor artifacts, especially at lower resolutions. It's not always perfectly clean.
Okay, fair enough.
Another is computational cost. Generating these really high-res models is still demanding, needing hefty GPU power.
Understandable.
And finally, they mentioned that getting better control over the generated interior structures and improving their quality is still an active area for research.
So refinements needed for boundary smoothness, efficiency for generation, and more control over the insides. Sounds like typical but important next steps for this kind of work.
Absolutely. But what's really significant here is how SparseFlex combines these different ideas. The sparse representation itself, that clever frustum-aware training, and the well-designed VAE architecture, it really highlights how rethinking the core representation and the training process can lead to major breakthroughs in a field like 3D modeling, which is notoriously difficult.
Okay, so let's quickly recap the core innovations for everyone. First, that sparse voxel structure. That's key for efficiency, enabling high-res modeling and just inherently handling open surfaces, moving beyond dense grids and those tricky watertight conversions.
Definitely number one.
Then, the frustum-aware sectional voxel training. That's huge for managing memory, getting up to that 1024 cubed resolution, but also quite remarkably allowing reconstruction of interiors using just rendering supervision by focusing learning on the currently relevant voxels. That felt like a real haha moment.
Agreed. That interior reconstruction capability is particularly novel.
And then there's the SparseFlex VAE architecture itself, the whole pipeline. Point cloud input, sparse voxelization, the point net grabbing local features, the sparse transformer encoder, then the decoders predicting the SparseFlex parameters, and those self-pruning upsampling modules boosting resolution and cleaning up open surfaces, all trained end-to-end with differentiable rendering.
It's a really well thought out system.
And finally, building on that VAE, the image to 3D pipeline, using that structured flow model for a coarse guess and the structured latent flow model to refine it in the latent space, showing real potential for generating detailed 3D from just 2D images. Those results, 82% less chamfer distance, 88% higher F-score, especially on tough datasets like Deep Fashion 3D, really underline the achievement.
For sure. But as we noted, the limitations, potential artifacts, compute demands, interior control, they remind us that this field is still moving fast, lots of exciting work still to be done.
So wrapping up this deep dive on SparseFlex, it really makes you think, doesn't it? With techniques like this emerging, capable of handling such complex geometry and topology, where does 3D content creation go next? What does this mean for VR, AR, digital design, maybe even robotics or simulation? Definitely something to ponder and keep an eye on. Thanks for joining us for this deep dive.